Next presentation will be by Bruce Randall. He'll be talking to us about black body radiators for calibration. Go ahead, Bruce.
Oh, hello, everybody. And that's what we're talking about, black bodies for calibration. Let's see if I got this okay. First, this is from the Vultures Roost Radio Astronomy Observatory. That you can see how I got my name. They kind of hang around there and they keep the roads clean, so they're fine. Okay, so what is a black body radiator? It's something that will absorb all electromagnetic waves that hit it at any angle of incidence, and it radiates electromagnetic waves exactly proportional to its physical temperature in Kelvin, which is what makes it potentially useful for a calibrator. It will also show zero reflection, that if you aim a radar at a perfect black body radiator, you would not see it there at all. It's total zero reflection. Oops, wrong area. Okay, here we go. A bit more about it. Most of the items that are a black body are actually effectively black over a quite limited range of wavelengths. So it has to be proper for whatever wavelength you're using in the radio range. An example of that would be titanium dioxide white paint. In bright sunlight, it's not a black body radiator at all. It's an almost perfect reflector of light. But yet in the deep infrared and radio wavelengths, titanium dioxide white paint is pretty close to a black body. It's a matter of wavelength there. An important thing for black body radiators trying to calibrate a radio telescope with them is we have the, if you move the temperature, or excuse me, move the wavelength around, the temperature and the amount of radiation track each other very good over the radio range. As you get into infrared visible range, you begin to run into a lot of complicated physical phenomena. There are a couple chapters in the typical physics book on what's happening there, but for our purposes over the radio range, they're fairly flat, which is an important factor. Okay, calibration adds control, involves adding a controlled amount of temperature at or near the antenna of a radio telescope, such as dragon, electromagnetic waves, power meter. And well, one of the things, calibration temperature from a dragon might be a little bit too high. And calibration temperature is likely to be pretty unstable because dragons are supposedly moody creatures. And I guess you could say, dragon, well, is that truly a black body radiator? Well, it's imaginary. Does it only show up in the imaginary channel on your DSP thing? I don't know. But anyway, that is the dragon robot at Fürstenwald, Germany. If I said that right, anybody who speaks German will probably cringe at my pronunciation. But anyway, it's near the Czech border, and they're very big into dragons. So I got a picture of it when I was visiting there. It's significant flamethrowers that are propane powered there. Anyway, so we're going to switch over to a microwave absorber. They're a little less moody and whatever. They're the temperature, the physical temperature. If it's a good absorber, physical temperature tells you what the calibration temperature is. You'll have it over the whole field of view of the antenna, and that works well. That turns up with any significant size antenna, a quite large item there. But if you measure the physical temperature of it with an accurate thermometer, and it's truly a black body radiator, you know what its radiation is in the radio range. But you do need a very low reflectivity on it for it to work. Any reflectivity will throw in some error there. And used like that, it must cover the full field of view of the antenna. Okay, I'll talk about absorbers just briefly. That you look at things that are used for absorbers in industry, like you look at the anechoic chambers where they check FCC 15 testing and that kind of thing. The walls will be covered with those cones, which are an absorbing material. And because an electromagnetic wave coming in there, as it hits the cone, the impedance changes as it travels along the cone. And causes, minimizes reflection. So even though the absorber may not be perfect, the result of it is very close because of the shape of the cones. Okay, we need really, for calibration, we need a total absorption at normal to the dish surface or the radio temperature and physical temperature will no longer track. Okay, lots of times for us, the best thing available is a calibrated forest, a very dense bit of vegetation at known temperature at 1400 megahertz, at least through 10 or 12 gigahertz range. It's pretty flat, and it's a pretty good indication. It's not perfect, but it's available. So I call that my calibrated forest behind me, calibrated, put that in quote marks maybe. Okay, so then think, well, what is calibration? I thought, well, you're talking about calibration here. Need to say, what is it? So I looked up on Wikipedia and said, a measurement technology and metrology or calibration is comparing something with a known standard, basically, and verifying that it matches the standard. Okay, so of course, an instrument has units of measure, and that's something we need to be careful of. I mean, you could measure currents in coulombs per fortnight. That is a legitimate measurement of currents, and it's in the area near a microamp. So you could actually use coulombs per fortnight on measuring leakage current on IC pins. So it'd be absolutely insane to do that, but that's a legitimate unit. But you want units to be useful. Temperature and Rankine, I think I'm saying that right. The Rankine scale has the step size of Fahrenheit, but it goes through absolute zero, just like Kelvin does. And it came about when they started designing steam engines here. They needed to know where absolute zero was, and they were Fahrenheit scale. So in came the Rankine. We are not going to say this preamp is so many Rankine temperature. No, it's so many Kelvin temperature, useful unit. Other thing we got to watch is on an instrument. Sometimes we get a measurement with 52.53873. Comes up on the display, so people want to write that number down. It reminds me of working with an electronics lab. And you see a student go and they take a 5% resistor, measure the voltage across it with a 1% accurate voltmeter, and then they bang it in their calculator and they give you 8 digits of precision on the current in the resistor. I mean, hold it a minute, nothing can be more precision than the combination of the parts. So we want our instruments to be in Kelvin normally for calibrating radio telescopes. And you want to carry the right number of digits. Maybe beyond tenths of a Kelvin is definitely nonsense for us. So don't carry excess digits, carry the ones you need. Okay, this is a book I bought a few years ago. It's unfortunately out of print. Copies on eBay are $100 now, but that was a very good reference. They were written up on the subject of calibrating radiometers for such things as surveying ice thickness in the Arctic and other such stuff. A couple of Scandinavian guys wrote the book, but they have a big